Hello everybody, welcome to Shaders Monthly. Today we are going to talk about deferred shading and implement a first simple deferred shading pipeline in GLSL. Deferred shading is a two-stage process. In a first render pass, we render the geometry and material information into several 2D textures. This collection of textures is often called the geometry buffer or G-buffer for short. The G-buffer can comprise a texture for the 3D position, surface normals, base color of the material, roughness, and so on. In a second render pass, we use the geometry buffer to perform the lighting calculations. Let's take a look at the OpenGL pipeline and talk about the difference between classic forward shading and deferred shading. As we have discussed in previous episodes of Shaders Monthly, classic forward shading works as follows. Input to the OpenGL pipeline are 3D meshes that are represented as a collection of triangles. The first stage of the OpenGL pipeline is the vertex shader, which is called in parallel for each input vertex of the mesh. In the vertex shader, we transform the vertices and per vertex surface normals of the mesh into the camera coordinate system. From the camera coordinate system, we project the vertices into the camera image, as discussed in detail in episode number 2 and 3 of Shaders Monthly. After the vertex shader, the pipeline performs primitive assembly. The projected vertices of the mesh are shown in red. For every 3 vertices, a triangle is created. This stage of the pipeline also performs per vertex post-processing, which includes clipping, perspective division, and viewport transformation. After the clipping and perspective division step, the coordinates in all 3 dimensions are in the range from -1 to 1, which is why they are called normalized device coordinates. The viewport transformation then scales the output such that the positions of the vertices are given in window coordinates. This means that the vertex positions in the X and Y direction are specified in the 2D pixel raster of the output image. Next, the rasterizer determines which pixels in the output image are covered by the primitive and calls the fragment shader for each output pixel. In addition, the rasterizer performs interpolation of each per vertex attribute that we have specified in our vertex shader. This means that each out variable of the vertex shader is interpolated over the area of the triangle, and we get the interpolated value as an in variable of our fragment shader. This gives us the interpolated vertex position, surface normals, texture coordinates, and so on for each pixel. Furthermore, the rasterizer interpolates the per vertex z-value. The z-values depend on the far and near clipping planes of the camera frustum. As we have discussed in detail in episode number 2, the z-value is in the range from -1 to 1 in normalized device coordinates. By default, this range is converted by linear mapping to the range from 0 to 1 in window coordinates. The per vertex z-values get interpolated by the rasterizer, and we can access the interpolated per pixel value in our fragment shader. When we perform forward shading, we use the given interpolated information in the fragment shader, such as 3D position, surface normals, or texture coordinates, to evaluate the lighting. The interpolated texture coordinates allow us to read the material parameters from the textures. To calculate the lighting in the fragment shader, we iterate over all the light sources. For each light source, we calculate its irradiance at the current 3D position and multiply the irradiance with the BRDF. The BRDF models the material of the surface. For example, we could use the Phong model from episode number 4, which is shown here, or the PBR microfacet BRDF from episode number 9. The multiplication of the irradiance and the BRDF gives the radiance LO in the view direction V that is produced by the light source. The resulting individual radiance contributions from each light source are summed up and we get an output color. If there are many lights in the scene, this loop over all light sources can be computationally expensive. The output color of the fragment shader is written to the corresponding pixel of the output image. The output image is also called the frame buffer. But before a color is written to the frame buffer, the fragment has to pass several tests. Most importantly, if the depth test is enabled, the color is only written to the frame buffer if the current fragment is closer to the camera than previous fragments written to the same pixel location. This means it is only written if the interpolated z-value is smaller. Consequently, the output color that we have computed in the fragment shader may never reach the output image. This is obviously a waste of computation time. In practice, this is not as bad as it sounds. The GPU can optimize the pipeline and can perform an early depth test. The GPU can check the depth value before executing the fragment shader, and the fragment shader is only evaluated if the depth test is passed. Of course, the GPU can only perform this optimization for opaque surfaces and when the depth value is not modified in the fragment shader. The early depth test is most efficient when opaque surfaces are rendered in a front-to-back order. With this in mind, to reduce computation, we should pass meshes with opaque material that are closer to the camera first into the OpenGL pipeline. This reduces the overdraw in the frame buffer. Here's an example. Let's say we have this medieval village that consists of several buildings. Each building is a mesh that we can feed into the pipeline. The CPU host application can sort the meshes according to their distance from the camera. In the example at the top, we render from back to front, and here at the bottom from front to back. On the right, you can see the resulting overdraw. We can see that the overdraw is significantly less when we render opaque surfaces from front to back. We could further reduce the overdraw by sorting the individual triangles as well, but then sorting on the CPU is likely to be the next performance bottleneck. By the way, if we have transparent surfaces, they should be rendered in a back-to-front order, not front-to-back. We render the opaque surfaces in the background first. Their output colors are written to the frame buffer. In the example shown here, we render all the opaque surfaces of the car first. Once this is done, we can render each transparent surface on top by alpha blending the color from the frame buffer with the color of the transparent surface to get a see-through effect. In this example, we first render the transparent mesh of the windshield, the right side window, the left indicator glass, and so on. We continue from back to front until all the transparent surfaces are drawn. Of course, this approach only works if we don't have interpenetrating transparent surfaces. So the take-home message is that we should render opaque surfaces in a front-to-back order to reduce overdraw. And we render transparent surfaces in a back-to-front order to enable alpha blending. Now, let's talk about deferred shading. As the name suggests, in deferred shading we postpone the shading to a second render pass. In the first render pass, everything stays the same until we reach the fragment shader. In the fragment shader, we do not perform the expensive lighting evaluation. Instead, we write all the information, which is required to perform the lighting evaluation later, into the corresponding output pixel of the frame buffer. So we have to store per pixel position, surface normal, and several material properties. Typically, this information does not fit into a single RGB8 texture. So we use multiple render targets, called MRT for short. We create several additional empty textures. These empty textures are attached to the frame buffer. In the first render pass, the fragment shader simultaneously writes the output data to the multiple render targets. For example, positions, surface normals, base color, and additional material parameters. This collection of textures is typically called the geometry buffer, or G-buffer for short. Writing the necessary data into the G-buffer is much faster than evaluating the lighting, especially if there are many light sources in the scene. When we write to the G-buffer, the depth test is enabled. And once all the triangles are rendered, each pixel of the G-buffer will contain the geometry information for the surface that is closest to the camera on a per pixel basis. In the second render pass, we need to evaluate the lighting for each pixel. A global directional light source typically affects every pixel on the screen. The same is true for image-based lighting. To perform the lighting calculation for each frame buffer pixel, we can simply pass a single screen-sized quad into the pipeline. If the quad covers the range from -1 to 1 in the x and y direction, it is already given in normalized device coordinates. So the vertex shader has to do almost nothing. It just passes the unmodified vertices of the quad further down the pipeline. The viewport transformation then scales the quad to cover the entire screen. The rasterizer processes the screen-sized quad and calls the fragment shader for each frame buffer pixel in parallel. In the fragment shader, for each output pixel, we read the information from the G-buffer at the location of the output pixel. We get the geometry and material data of the closest surface from the G-buffer, perform the lighting calculation, and write the result to the frame buffer. The big advantage here is that we have no more problems with overdraw. At least not in the second render pass, because the depth test in the first pass ensures that we only keep the closest surface for each pixel. This is a clear advantage compared to forward rendering. A disadvantage of deferred shading is that we need some additional texture memory to store the G-buffer. Another disadvantage is that the texture units have to perform more read and write operations. Deferred shading can be very useful when there are many small light sources in the scene. Let's use the medieval village again and assume that the villagers have placed many torches along the main street. Each torch is modeled as a small point light. As we have discussed in episode number 4, the irradiance of a point light decreases quadratically with distance. So the irradiance drops quickly, but it never reaches zero. For real-time performance, we should only evaluate lights that produce a significant irradiance at the current location. Therefore, real-time rendering engines typically have a maximum light range. If the distance to the light is larger than the maximum light range, the irradiance is set to 0 using a smooth windowing function. Defining a maximum light range allows the culling algorithm on the CPU to remove all point lights that are outside of the camera's view frustum. In this example, the view frustum of the camera is drawn in purple. The frustum is bounded by the camera's near and far clipping planes. Any point light outside the frustum contributes nothing and can be ignored. This culling of light sources with the view frustum can be done for both forward shading and deferred shading. However, with deferred shading we can go even further because we have the depth buffer. As you can see here in the camera image, most of the torches are occluded by the buildings from the camera's point of view and can also be skipped. The idea of depth buffer based light culling is to keep the depth buffer from the first render pass active. For each light source we render a bounding volume around the maximum light range. This could be a bounding box or a bounding sphere. In the shown example, a bounding icosphere is used. Let's move the camera over here to see what's going on. On the top left you can see the rendering output. And on the top right the depth buffer together with the color-coded bounding spheres of all 25 point lights that are used in this example. With the depth buffer from the first pass active and backface culling enabled, we push the bounding spheres into the OpenGL pipeline. Let's observe the effect of adding each point light source. This slider controls the number of light sources that are evaluated. Down here on the left you see the radiance contribution of the current light source. And on the right the output pixels for which the fragment shader is called and the lighting calculation is performed. This is the first light source. Now we add the second, the third, the fourth, and so on. With the depth buffer active, only those pixels of the bounding sphere that are not occluded will reach the fragment shader. We evaluate the lighting for the current light source only for these pixels. This saves a lot of computation compared to evaluating the lighting for all pixels of the screen. Let's move the camera back to its original location. When we iterate over the point lights here, we can see that large chunks of the projected bounding sphere are occluded, so we need to evaluate only a very small portion of the screen. In summary, this approach allows us to perform a per-pixel culling of light sources in the Z direction. This culling of lights is only possible because of the depth buffer from the first pass. This is the main reason why deferred shading can significantly improve rendering performance. Okay, let's summarize our findings by comparing the properties of forward and deferred shading. Deferred shading requires 2 render passes. The first pass must be completed before the second pass can be executed, which introduces an additional barrier for the parallel execution. A big advantage of deferred shading is that we have no overdraw in the second pass. There is overdraw in the first pass, but the computational cost of an overdraw is much lower. With forward shading without an additional Z prepass or other measures, we can only perform light source culling based on the camera frustum. With deferred shading, the lighting calculation in the fragment shader of the second pass is only executed if the pixel is within the projected bounding volume of the light source and passes the depth test. This means that we can handle many more light sources in the scene if each light source only affects a small area of the screen. A disadvantage of deferred shading is that we need more texture memory. It also generates more read and write operations on the memory. GPUs can reduce memory latency by switching to another parallel thread or by caching. Nevertheless, for deferred shading, the overall performance might be limited by the bandwidth of the memory access. Another disadvantage of deferred shading is that it cannot handle transparent surfaces because only the closest surface to the camera is known when we evaluate the lighting in the second render pass. Forward shading can deal with transparent surfaces, but only if the surfaces are not interpenetrating and are sorted from back to front on the CPU. Okay, this is the end of the theoretical part. We move on to the practical part and implement a deferred shading pipeline. We use the GSN Composer at gsn-lib.org as our shader editor. The GSN Composer is a web-based tool that I created especially for teaching shader programming. But you can use any other shader editor as well. We write pure OpenGL GLSL code that you can use anywhere. Links to examples that execute the same shader code using C++ or Java can be found in the video description. The implementation is based on the example that we created in episode number 9. Click on Project and type in the name Shaders Monthly 09 and click on Open Existing. Then open the graph Microfacet BRDF and press Play in the time control panel. The example from episode number 9 uses a Microfacet BRDF and a directional light to render a stone demon. Here's a shader node that performs the rendering and contains the shader code. This input node contains the mesh data of the stone demon. Furthermore, we see that 4 textures are used: diffuse albedo, roughness, normal, and emission map. The mesh is illuminated with a single directional light source. The light direction can be changed here. Currently, our shader node performs classic forward shading. We open the shader editor and inspect the shader code in the fragment shader. Down here in the main function, we compute the irradiance of the light source and multiply it with the BRDF. This gives us the radiance. The radiance is converted into the sRGB color space by gamma compression using our lin to RGB function. If we had more than one light source, we would have to loop over all the light sources here. So for example, we could put a for loop here and add the contribution for each light source to the radiance for each loop iteration here. But before we make any changes to the shader, let's make a copy of the shader node because we can reuse much of the code for the second render pass. We open the first shader again. For deferred shading, instead of evaluating the lighting, we should write a G buffer. We don't need to change anything in the vertex shader. There are three out variables. outVec2TC for the texture coordinate of the vertex, outVec2WFN for the vertex normal in world space, and outVec3VertPos for the 3D position in world space. The texture coordinates are just passed on. Here we calculate the per vertex surface normal in world space, and here the vertex position in world space. These three out variables are interpolated in the rasterizer. In the fragment shader, we get the interpolated values as in variables, as you can see here. We need to define our G-buffer. Here we have defined the output variable of the fragment shader. Currently, we have only a single RGBA render target, outVec4 outColor. Let's create multiple render targets. Layout location equals 0, outVec4 outNormal. Layout location equals 1, outVec4 outPosition. Layout location equals 2, outVec4 outBaseColor. Layout location equals 3, outVec4 outMaterial. Layout location equals 4, outVec4 outEmission. For each out variable, the GSN Composer creates an RGBA output image for the shader node. The location index, which we assign here, maps the out variable name to the index of the output image. If you use this shader code outside of the GSN Composer, you have to create an RGBA texture for each out variable and attach it to an off-screen frame buffer in your host application. This can be done with the OpenGL GL Frame Buffer Texture 2D function. The C++ or Java source code in the video description provides an example. We can simplify the shader. These three uniform variables are related to the lighting and can be removed. We don't need these functions. And these functions are related to the BRDF evaluation and can be removed as well. In the main function, we delete almost everything. The only lines that we keep are for the application of the normal map. Apply normal map. We have used the apply normal map function in our shaders without really discussing it in detail. I will skip this today, but I am going to explain normal maps in the next episode of Shaders Monthly. Now all we have to do here is to write the interpolated surface normal in world space to the first render target with index 0. Render to target 0 outNormal.rgb equals n. We could use the alpha channel as well to store some information, but we set it to fully opaque here by assigning a 1.0. outNormal.a equals 1.0. This way the texture is fully opaque and we get a visually clean output. The VEC3VertPos variable contains the interpolated 3D position in world space. We write its x, y, and z value into the red, green, and blue channels of the render target with index 1. Render to target 1, outPosition.rgb equals VertPos, outPosition.a equals 1.0. Next, we read the base color from the texture and write it to the render target with index 2. Render to target 2, out base color equals texture base color texture TC. The RGB base color is a parameter of the material. For dielectrics, the base color contains the RGB values for the albedo, which is the amount of diffuse reflection. For metals, the base color contains the RGB values for the Fresnel reflectance. We have discussed the details in episode number 9 of Shaders Monthly. In the next render target, we write additional material parameters. Render to target 3, outMaterial.r equals metallic, outMaterial.g equals texture roughness texture tc.r, outMaterial.b equals reflectance, outMaterial.a equals 1.0. For this model, the roughness parameter varies across the surface, so it is read from a texture. The metallic and reflectance parameters are constant and are therefore given by uniform variables. Furthermore, this 3D model has a texture for the emission of the surface. So for completeness, we write this out to a render target as well. Render to target 4, out emission equals texture emission texture TC. Apply and close. Our shader node has 5 outputs. Let's display the result here on the right. We have surface normal in world space, position in world space, base color, metallic, roughness, reflectance and emission. Okay, our gbuffer shader is ready. I have one last thing that I wanted to show you before we continue. Instead of writing the 3D position here, we can also write the depth value. Given the camera parameters and the z value, we could compute the 3D position in the second render pass. This is an option to save some texture memory. You can access the z value in the fragment shader via the built-in glfracchord variable. vec3 glfracchord.z. Apply code. Okay, this seems to have worked. We see the depth value as a grayscale value in the output. We undo this change and write out 3D positions again. Let's implement the shader for the second pass. We need to render a screen size quad. Press the Create button and go to 3D, Compute, Generate, Plane. This creates a quadratic plane mesh that goes from -1 to 1 in x and y direction. We connect this mesh to the mesh input of our shader. We open the shader editor. Because our input mesh already goes from -1 to 1 in x and y direction, the vertex shader needs to perform no transformation. We can delete these uniform variables. And we can delete these 2 out variables. In the main function, we pass the texture coordinates to the out variable tc. And real position equals vec4 position 1.0. In the fragment shader, we delete the unused in variables. Then we need input slots for the 5 textures of the gbuffer. Uniform sampler 2D normal texture. Description equals gbuffer surface normal texture. Uniform sampler 2D position texture. Description gbuffer position texture. Uniform sampler 2D base color texture. Description equals gbuffer base color texture. Uniform sampler 2D material texture. Description equals gbuffer material texture. Uniform sampler 2D emission texture. Description gbuffer emission texture. We can remove the metallic and the reflectance uniform variable. Or this code can stay because it is related to the lighting calculation. In the main function, we now need to read all the parameters from the 5 textures. vec3n equals texture normal texture tc.rgb. We read the surface normal from the texture, so we can remove the computation here. vec3 vertpos equals texture position texture tc.rgb. vec3 base color equals rgb to lin texture base color texture tc.rgb. The RGB to lin function performs gamma expansion and is required here because we wrote the base color as sRGB values into the gbuffer texture. vec3 mat equals texture material texture tc.rgb. The metallic parameter is in the red channel of the texture. Float metallic equals mat_t.r. The roughness parameter is in the green channel of the texture. Float roughness equals mat.g. And reflectance is in the blue channel. Float reflectance equals mat.b. We can remove this line because the roughness parameter is read from the gbuffer now. And we can keep this line for the emission parameter. Okay, that's it. All parameters are now read from the texture. Everything else stays exactly the same. This code here performs the lighting calculation for the directional light that we have in the scene. Apply code and close. Now we hook up the 5 gbuffer textures. Furthermore, we need the light direction and the camera position in world space. Let's put the G-buffer and the result of the deferred shading pass down here. Perfect, it looks like everything is working as expected. This is the surface normal in world space, position in world space, base color, metallic roughness reflectance, emission, and the final rendering result of the deferred shading pass. Obviously, our G-buffer setup is a bit wasteful. We have not used the alpha channel of the RGB8 textures to store any information. Furthermore, in the GSN Composer, all textures have a floating point format, which means they need 32 bits per channel. 32 bits are not required for our parameters. 8 bits per coordinate for a surface normal might produce some quantization that is noticeable in the final rendering, but 16 bits per coordinate would be totally fine. There's no standardized format for the G-buffer. Every render engine does it differently, so there's no strict rule that we need to follow. In a real game engine, the bits of a G-buffer would be used more sparingly than in our educational example here. Okay, that's it for today. We have discussed and implemented deferred shading. If you have any questions, use the comments or get in contact with me. As always, if you prefer C++ or Java source code, this can be found in the video description. See you in the next episode of Shaders Monthly.